In Chapter 2, we'll consider some programming examples, area estimation, visualization of complex valued solutions for quadratic equations, and discrete Fourier transform along with short time Fourier transforms. Then we'll study computational algorithms and their convergence speed. And finally, in the chapter, we'll consider inverse functions along with exponential functions and logarithmic functions. Let's go to section 2.1. Area estimation of the region defined by a cluster curve. Here is a problem. It is common in reality that a region is saved by a sequence of points for some n positive number, x0, y0, x1, y1, and then the final point is xn, yn, which is the same as the first one. Then this point will represent a region. For example, this region can be approximated by these points. So maybe this is x0, y0, x1, y1, and so on. Turn around, and then the last one will be xn, yn. Here the question is, if a sequence of points represents a region, how can we compute its area accurately? Such a problem is quite common in reality, particularly once you are working on medical images such as the X-ray images or the cross-section of CT scan or MRI images. Then you may get segmentation to recognize some cells, like cancer cells, and you may try to get the area. And rather than comparing the area just by observation, if you can get the mathematical quantity of the area accurately, then you can make a better appeal to patients, and then the medical treatment can be more accurate and more reliable later on. Okay. Now, to derive the computational formula for the area computation, let's begin with a very simple example. Find the area of rectangle AB in x direction and in y direction from C to D. Then these 4 points. Okay, we know the area is horizontal distance and vertical distance multiplication, and this quantity can be written in this form: b times d minus c minus a d minus c, and we rewrite in this way. Okay, from here now b, okay, that is b value in x direction, and y direction d minus c is change in y along that vertical line segment. And also when x is a, the c minus d is change in y. If we try to turn around in this direction, that is a change in y is this one, change in y is c minus d. So it looks like here x value times change in y. So we may guess the area is given in this way. So yeah, this is now for each line segment, the center value of x, that is ith line segment. And so the center value of x is now for that one. And then change in y is here 0, so has no contribution. But for that one, center value of x is same as always here now, b, and changing y is d minus c. And here, center value of x is in fact ab over 2, the addition over 2. However, changing y is 0, so that there is no contribution. Now here for x value, midpoint of x is now a, and changing y is c minus d. That is exactly this formula. So we may guess this one. Now, for this guess, let's check the reliability. Okay, and now we will try to find the area of triangle. Now we know the area, that is half b minus a, the length of this bottom, and d minus c is now the height. So the half times bottom length times height. We know that. Now we'll try to check if this formula is correct. Okay, and if we follow this formula, then here center value of x for this line segment is a plus b over 2, and in y direction the value is c and c, so that's c minus c. Okay, for that line segment, so we are always running in this counterclockwise, so that if we run along with a boundary, then you will see the region left hand side. That rotation is called positive orientation. Anyway, for that one, the center value of the x is b plus b over 2, and that is b and b over 2, and changing y is d minus c. Okay, now for final segment from here to there, that is now center value of x is, okay, a and b, addition divided by 2, and changing y is c minus d. Okay, the first one is 0. Now, okay, that one is p times d minus c, and then now that is now the same here, and we rearrange it, and by using some algebra we can reach at this one, and then eventually we can get the same result already we know here. Here now we have note here, horizontal line segments makes no contribution to the area. Okay, and here, so that for this example, our guess the formula is correct. Now let's verify once more. Okay, now for this region, this is quite similar to the mark for Mississippi State University. Okay, for that one, the total area of this rectangle is 36, and the area over there is 2, and there's 4, so that 36 minus 6 is 30, so that the this shaded region is in maroon color, the area is 30. Okay, now let's begin from here, and then let's try to collect just non-zero contributions. Okay, zero contribution. For that one is now x is 2, y changes 3. That's exactly that one. For this one, now midpoint value, mid value of x is 2.5. Changing y is minus 2. Is go down by 2. Okay. For this line segment, now mid value of x is 30.5, and changing y is 2, and for that on midpoint of x value is 4, and change is 3. So that is exactly this one, no contribution, and then x value is 6, and y change is 6, so that this one, Now for there no contribution for this one. Now x value, mid value is 3.5, y change is -2. For this one, now mid value of x is 2.5 and change in y is 2. So that is exactly this one. Okay, and here there's no contribution and mid value of x is 0, and even though change in y is -6, x value is 0, so that for that vertical line segment there's no contribution. Okay, now we simplify these quantities, then we can get 30. Okay, so even though very complicated shape, the formula must be correct. Okay, here, so we summarize the above work in this way. Let a region R be represented as a sequence of points, and x0, y0 to x and yn, and the first and last points are the same, so that eventually these points will make a closed curve locally line segment. Okay, now the Li is the ith line segment connecting xi minus 1, yi minus 1, and xi, yi. So there are n line segments. Then the area of R, the region, can be computed using the formula here for each line segment. For in this case, ith one, xi star is midpoint of x, and delta yi is in change in y. So that's the formula, and it'll be correct for any shape. And once the region is represented by as a sequence of points in this way, then it can be used to get the area inside of the curve. The formula is a result of Green's theorem for the line integral and numerical approximation. Okay, if you go to vector calculus, then the application of the Green theorem, you'll see here now area of region D is now same as integral closed curve and x dy. If you learned already the vector calculus, then you may memorize this one. Okay, now here, okay, C is the curve and D is region inside of a curve. So it is an application of Green theorem. And once the boundary is locally line segment, piecewisely line segment, then this formula is exact formula. There's no error involved. But usually the boundary is not local linear, then you may choose very dense point along the boundary, and you may try to approximate the boundary with locally linear. Okay. Okay, we'll see another example here. We'll generate a data set, save it to a file, and read it to plot and measure the area. Okay. Let's generate a data set that represents the circle of radius centered at the origin and radius 1. Then we can make in this way xi, yi is now this is cosine theta I and sine theta I. The theta I is I times 2 pi over n. Then here the first point and last point must be the same. So it is representing the circle and locally linear. Okay, and we'll try to analyze accuracy improvement of the area as n grows. The larger n you choose, the more accurately the theta would represent the region. Okay, here we have a program. Now we start with n equal 10, so 10 subintervals, and we make here now the theta. Okay, that is, we are choosing n plus 1, so that now eventually theta, it starts from theta 1 in MATLAB, but in mathematical notation, it is same as theta 0, but 0 to 2 pi and n plus 1 point, which means there are n subintervals, and along with that, cosine theta, sine theta, and the theta is made. So we get an n plus 1 the points, and representing n subintervals. Okay, for that one, first we make a figure along with red one and solid curve. Okay, and then we save it now into circle.png, and also the data is saved into circle data.txt text file, and by using CSV write. And here, when you save the data in a metric, and you can use here write metric, and then delimiter can be chosen. The default one is comma, but now in this case, if you are using this line, then the space will be delimiter. Okay. Now, okay, after saving the data, we try to read the data by using load command, and save it in data, and first column will be x and second column will be y, and again we try to make a plot along with blue color and dash the curve. Okay, and we save the end, and of course over there by using area of closed curve command, okay, that will be implemented in separately in file, and we can get area here, and then the area is printed out along with the number point n. Okay, here that is the curve along with n equal 10, representing the approximating circle of radius 1, and that is now data is saved in red, and then here I make the shape. Of course, two must be the same. Okay. Now here we have the output when we are choosing n is 10, 20, 40, 80, 160. Then the area is approaching, in fact, is increasing and approaching to pi. Here we measured the misfit from pi, and there is error, and now error is becoming smaller, but in fact become a quarter as the number of points is doubled. So which means that it is second order convergence. Okay. From this example, and you learned how to generate the data set, to save the data into a file, and read a data file, and also when we try to plot the data, we should set figure environment, so that you learn how to set figure environment, and also how to call functions. This is a simple example of area estimation defined by a closed curve. Okay. Thank you.